Right, functions and surfaces. So, what you're used to seeing, of course, I'll go right to the whiteboard just for a moment. You're used to seeing functions of x, okay? And you've seen that for a long time. And when you're dealing, if y is a function of x, that's some curve in the xy plane. But in applications, oftentimes we want to have the function be a function of multiple variables, for instance, x and y. So if you have a function f of x and y, okay, what would you set that equal to? What would be the natural variable to set that equal to? That's right, Ellie, z. Okay, so in calculus 1 and 2, you had you had y as a function of x, and if you plotted xy coordinates, you'd get a curve in two-dimensional space. But now you have x and y; those are your independent variables, and your dependent variable is z. And so you see, if you plot coordinates x, y, z, and you plot a lot of them, you're going to create a surface. Okay, so now z is a function of x and y. Just like in in your other math classes that you've had before, you have a function and the function of x, and there's a domain and a range. Well, we can have a domain and a range when we have a function of x and y as well. Okay, so let's go ahead here and look a little bit at some nice examples in the book. All right, so let me switch over here back to the book. Okay, so I want to go right to an example here. All right, and I guess I had some things highlighted. There we go. Okay, hold on. Okay, so domain and range. Domain and range. So here, let's say you have a function that of x and y that equals 4x squared plus y squared. Okay, well, the function is defined for all possible ordered pairs of real numbers. So the domain it's denoted as R2, which is the entire xy plane. Okay, so it's all real x coordinates and all real y coordinates. That's R2. But the range of the function is just going to be this interval from 0 to, well, hold on, I don't want that necessarily highlighted like that. Hold on, let me try to do it. It's kind of picky. There we go. Yeah, so this function, f of xy equals 4x squared plus y squared, that function is always positive, right? So the z values are always positive. So the range is going to be all non-negative real numbers. Okay, so that's like a domain and a range. Are there any questions on example 1? All right, well, let's move along then. Let's keep moving along here. So here, okay, let me just remove this. So in example 2, they want you to sketch domains for the following functions. So here in A, you have an interesting function. In example 2, you have f of xy equals the square root of x plus y plus 1 over x minus 1. Okay, so you have a rational function here, a rational function. And, you know, what would limit the domain? Like what x value cannot be in the domain? Okay, that's right, Ian. You can't have a denominator of 0, so x equals 1 would not be in the domain. Now, what about the square root above? The inside the square root, x plus y plus 1, that can't be negative. Good, that's right, Hyunyu. So that means that, well, x plus y plus 1 has to be greater than or equal to 0. Okay, so you have two conditions that have to be met. And incidentally, just so you know, if we were to evaluate the function at 3, 2, we would just put in the values, right? And solve for the function. But let's take a look at the here at the picture of the domain. Okay, here's a picture of the domain for this function. So x equals 1 is an asymptote. So the domain, of course, is in the xy plane, right? It's a subset of the xy plane because our function's a function of x and y. So x equals 1 is excluded from the domain. And then we need that x plus y plus 1 be greater than or equal to 0. Okay, which means, I mean, if I put it on the whiteboard here, hold on, we have that, hold on, let me get my stylus. I'm getting used to this stylus now a little more. I'm getting more comfortable with it. X plus y plus 1 would be greater than or equal to 0, which means that y would be greater than or equal to negative x minus 1, right? Okay, so if we draw the line, negative x minus 1, I mean, this would be our boundary. So if we go back to the picture here, there's the, there's that boundary line, y equals negative x minus 1. It's a x plus y plus 1 equals 0. It's the same as y equals negative x minus 1. So that's a line passing through y-intercept of negative 1 with slope negative 1. And all the points above it are going to be in the domain. So that's a picture of it. That's a picture of it. And if we were to, graphically, well, if we were to just sort of write out what the domain is, that's what the domain would be. Okay, so, we can find domains. We can find domains. It's harder, right? But we can find domains, and we can also find ranges too. But here they just wanted to find the domain. So I just want to do part A. You can look at part B if you want. But, why do we need these? Well, are there any questions? Any questions on this? On example 1? Okay. Okay, well, let's move on then. So, okay. Why do we need functions of two variables? Well, here's an example. Example 3, wave height as a function of wind speed and time. So the way, I don't know if you've maybe noticed this, but the wave heights in the open sea depend mainly on the speed of the wind and the length of time that the wind has been blowing at that speed. Okay, how many have might have noticed that if you've been to the ocean. I mean, it might not be something you notice, but how many have noticed that when the wind's greater, higher, the height of the sea, the waves are larger? How many certainly have noticed that? You know, like a hurricane, you know, right? Does that make, so does it make sense that the wave height is a function of the wind speed and the time that the wind has been blowing? Does that sort of make reasonable sense? Sure, absolutely. And what they've done is that meteorologists and oceanographers have taken observations and measurements and produced it in this little table here below. Okay, so you know you have the wind speed, okay, on the left, and you have the duration on the right. And then in the white boxes are the wave heights. Okay, so this is how you read this. So like for instance, when the wind speed is 15 and the duration of the wind is 10 hours, what is the wave height? What's the recorded wave height? No, let's do it this way. When the wind speed is 20 knots, and that's gone on a duration of 10 hours, what's the wave height in feet? How high are the waves? Good Hyunyu, 7 feet. 7 feet. Now, if we focus on wind speed, keeping it constant at 20 knots, and we move along the row, what seems to happen to the wave heights as the duration increases in hours? Are the wave heights going up? Are they going down? Wave heights seem to go higher. That's right. And we can also study the graph vertically. So like for instance, let's say that the duration is 10 hours. Let's t equals 10. If t equals 10 hours and the wind speed is 40 knots, what's the wave height equal to? 21 feet. Okay, and incidentally, what if the now hold on here, h, they're saying here, now we're going to be a little more formal. I mean, we're fine, but suppose we want h as a function of v and t. Let's say that v is equal to 50. Okay, the wind speed's 50, and the duration is 30. What would the function value be? What would the wave height be when wind speed is 50 and duration is 30 hours? 45 feet. That's right. Good. And that's what they have here below. You see, they have they wrote that out there a little bit. They wrote that out. So estimate's 45. So you know, there's an example of you know, where you really, if you want to model wave heights, you really need functions of a function of two variables, and sometimes you even need more variables than that. Okay, and you know, welcome to statistics. Okay, but at any rate, we'll stick to what we're doing here. So, okay, now, you know, we want to be able to graph functions, right? We want to be able to graph these. We have here a table. We have here a table. And based on that, we can find function values. But what if we were given a function? Okay, so Well, I mean, it's a function of x and y. So in figure 3 here, they have a domain, and the function of x and y, well, I want to say this the right way. Look at the domain. The domain is that region D in the xy plane, and then your function of x and y is the z value. So if you take the x, y, and z value and plot them, you're going to get a surface S above the region D, above your domain. Does that make sense on figure 3, what you're seeing there? Who's feeling reasonably good? Okay, Mario's good. And Yunu's good. All right, all right. Well, you know, so we can graph some functions, right? We can graph some functions. Like, so for instance, a simple function is the function f of xy equals 6 minus 3x minus 2y. Okay, this is the this is actually example 4, what we're doing here. Let me see if I can maybe bring that up a little bit. Yeah, graph that function. So, you know, how are we going to graph it? Well, we know that this is the equation of a plane because z is equal to f of xy, and z equals 6 minus 3x minus 2y. That can be written as 3x plus 2y plus z equals 6. So that's a plane. So if we graph the function, the easiest way might be to plot, to find the intercepts of the plane, which they do in figure 4. So once you've anchored down the x, y, and z intercepts of the plane, you can just draw a portion of the plane like they've done there. You know, it's a triangular triangular portion of the plane, but it gives you enough idea to get an idea of how that plane's oriented. Okay, are there any questions on that? On example 4? Okay, well, example 5, let's look at that. So example 5 here, okay, they want you to sketch a graph of this function, okay, where f of xy equals x squared. Now, normally you're used to that being a parabola, right? But this is a function of 2 variables, and you're saying that equals x squared. So it doesn't involve y, this equation. So, I mean, if we were to graph this function for every y value, z equals x squared. For every y value, z equals x squared. So to graph that would be basically, think about taking z equals x squared and moving it along the y-axis. For every value of y, z equals x squared. If you put all those parabolas together and attach them, you get what's called a parabolic cylinder. You get a parabolic cylinder.
Professor?
Yes, yes.
Whenever f of x comma y equals to x squared, then then you assume that all real numbers of y is still involved?
Well, you think of it like this. Good question. Okay, think of it like this. So, right, f of xy equals x squared. But you could think of that as x squared plus 0 times y. So z equals x squared plus 0 times y. So regardless of what y is, z equals x squared. Okay, so like when y equals 1, z equals x squared. When y equals 2, z equals x squared. sorry, comma there, when y equals 3, z equals x squared. So if you have a y-axis here, okay, and you have like, 1, 2, and 3, here's 0. Well, z equals x squared is, got to draw it right here. It's a parabola. A parabola in, if you think of like the xz plane, that's what the parabola looks like. But z equals x squared for all y values. And so if you connect those parabolas together, you see, you get a parabolic cylinder. See that?
Yeah, it reminds me of the first day of class that you said something about this. Okay, I get it
That's
now.
right. That's exactly right. You've had a little experience with that. Absolutely. And so, there you go. There you go.
Thank you.
You're welcome. And we have, of course, we have things where sometimes things get a little more complicated. And we have to use what are called traces to graph the function. And I'll let you look at example 6. I might actually, the section 9.6, that assignment, I may edit it. Well, I guess I may edit that a little bit based on what I get covered today. Okay, but the thing is, you see, they talk about like, for instance, like in example 7, they have a hyperbola. Okay, they have a they want you to graph this f of x y equals y squared minus x squared. And you see, the old-fashioned way of graphing these kind of surfaces is to the old-fashioned kind of way is to substitute in values for different variables like x, y, and z, and study what the traces are. So if you set x equals a constant, then like in figure 7, if x equals a constant, then z would equal y squared minus k squared. And so as k changes, you get parabolas with different y-intercepts. Okay, and so if you were to look at this, this surface with respect to the x-axis, you might have an idea of what it looks like. If like, look at the third picture. If you let z equals k, then you're going to get y squared minus x squared equals k. That is a hyperbola. How many has it been a while since they've graphed hyperbolas in maybe even high school, right? Since you've seen that. Okay, Ian knows what I'm talking about. Gordon knows what I'm talking about. But the thing is, you see, if you were to study this surface from above, a hyperbola is what you see there in that third picture. A hyperbola is like this kind of thing. That's a hyperbola. So it's been a while, right, since you've seen that. But the thing is, and I don't want to dwell too much on this, the old-fashioned way, of graphing these surfaces is to take traces and then look at the traces with respect to, the different traces, and then you put a picture in your mind together of what the surface is, and if you were to put the traces together, think about it and it's like putting a picture together, you would see that you would have a hyperboloid, and that's what you would get for this example 7. But you see, this idea of using traces to draw a surface only works for simple surfaces. I mean, suppose you had a surface like you see there in figure 10. See there in figure 10, these surfaces? How would you graph, like for instance, in figure 10a, you have the function xy, f of xy equals, in parentheses, x squared plus 3y squared times e to the negative x squared minus y squared. Okay, now that surface, you might be able to, based on the properties of the function, be able to recognize that the function dies down as x and y get large because of that exponential function there, that dampening function. But it's very helpful, of course, to have MATLAB help you graph that. So let me see here. Let me make sure I got this right. Figure 9, actually this is figure, they call it figure 10, but in my book it's figure 9. No, it actually is figure 10. It actually is figure 10. I'm going to have to change the file name, okay? I'll change the file name. But let me take you into Blackboard here. That's the first time I noticed that. But that's okay. That's okay. Let me take you into Blackboard and introduce you to a program that you will be using to help you with some of your 9.6 homework. Okay, so let's see, I don't want that. I don't know why it's doing that. Hold on. Let's get out of there. Hold on. Just give me a moment here, class. Okay. There should be no problem now accessing files in the syllabus or anything like that. No, that's not what I want. I'm going a little too fast. I'm moving a little too fast here. Let me slow down. Okay, let's get back to those announcements. Okay, so can everybody see the Blackboard okay? Maybe give me a thumbs up. Okay, excellent. So, thank you. So you see there's a link there called MATLAB Programs. Thank you, Juliana. Thank you, Hunyu. There's a link called MATLAB Programs. Click on MATLAB Programs, and then click here to see some helpful MATLAB programs. Click here. In section 9.6, there is a MATLAB program. Click on the link, and it'll bring up a MATLAB program that you can download. You can download. So if you will click on that link, who is seeing the MATLAB program? It says for figure 9a, but it's actually figure 10a. But who is clicking on that link and seeing a MATLAB program that they can download? Maybe give me a thumbs up if you're experiencing that. You should be seeing. Good. Let me see here. Let me see here. Sorry. One moment. Okay, let me find it here. Okay, good. That's right, Mario. That's right, Unu. Let me just. Okay, that's it. Okay. Man, hold on here now. Yeah, so you're all seeing that, right? Okay, so you can download that, and it's an M file, which stands for a MATLAB file. So you can download that and bring it into MATLAB. And I have my MATLAB open. Okay, I have my MATLAB open. At least I did. Hold on. Hold on here. Now, where's my MATLAB? Here it is. There it is. How many now have downloaded their MATLAB using the MATLAB installation instructions? Good, good. Now I'm gonna, good, Mario, and I know some other people are clicking and saying yes, thank you, excellent. To clear the command, there's a command window and an editor. So the program comes up in the editor. You want to type CLC in the command line if you want to clear your screen. And if you want to clear your variables, you type clear vars. Okay, so hopefully this is showing in the, yeah, it's showing in the recording. Clear vars, that clears your variables. And I'm going to take this program here. Okay, I'm going to take this program. Okay, I'm going to take the program. I'm going to copy it. And I'm going to paste it in the command window, and up comes a graph. So if you, let's see here, go to here, you should see this. How many are seeing a graph like, whoops, hold on, I lost it. Bring
Professor,
it back.
how do you get the command window to read? Or oh, okay, so we got undefined function systems for input arguments of type.
Well, what you want to do is, so in here in the editor, the program should run as is. There's no reason to edit it. So what you do is you load that M file into MATLAB. It'll go into the editor automatically. Like if you put that M file in your, if you like put it in your, I don't know, your Explorer or something, your personal files, and you click on it, it should open up MATLAB and put that file in the editor, just like you see. And you just copy and paste all the code on the command line, hit paste and enter, and it should produce the nice graph that that you saw.
I'm
How many did get this nice looking graph? How many did get that? Maybe give me a thumbs up if you're. That's exactly the graph that's in the textbook.
I see that.
Mara, did it? Go ahead.
Sorry, I noticed that you possibly, this possibly opened on a different window. So, like, whenever you run the command prompt, is that what's going to happen? It's going to open on a different window?
Yes, it will. The figure will come up. It'll come up on it'll be a pop-up. That's correct.
And running it is just simply like pressing enter or something? After you
I just copy the code, paste it in the command line, and then hit enter. Yes, that's right. That's right.
Thank you.
Okay. Maybe who did get this? Who did get this picture? If you've tried it, maybe if a few people got that picture, give me a thumbs up. I'd like to know.
Yeah, Professor, could I maybe share my screen and show kind of what my error message is?
Well, I don't want to do that. I don't want to do that. I want to see that after class.
Right.
I want to see that after class because I got to talk about. Oh, it gives you an error. Okay, hold on. I mean, put it in the chat window. Let's put it in that way. Marwan says requires symbolic math toolbox. Is that what it's telling you? Also,
no, my message is this one.
Okay, I'll put it this way. All right, I got it here. What? So here's my advice because I got to talk about the exam a little bit here before we go. But oh wait, we got 20 minutes. Wait, we got 20 minutes. We got 20 minutes. Okay, so let me just see if I can. Yeah, hold on. I don't want to ignore error messages. So let me maybe a piece of advice here. Hold on here. Where is that? Okay, what you could do, if it's not loading properly in the editor, you could just copy the code and type it in the editor if you need to. But this code will run. It will run. It is workable code. So I'm not sure what's going on. But I'll tell you what, Mario, let you share your screen as you asked here, because we have 20 minutes. I think we can take 5 minutes here.
Sure.
I'm going to make you a presenter, Mario.
Okay.
And so you now share your screen, and let's see what's going on.
Sure. Share contents and share.
Charles made a comment there.
There we go. Okay. Can everyone see my screen? Oh, well, now we've got an interesting infinite function there. Okay, so barring that, let me go to MATLAB. So I've typed in the code given in the editor, and
okay, no spaces, no spaces.
Okay. So I'll go ahead and delete the spaces. I copied that over to the command window, but this is the error message that I got there.
Okay, undefined function sims. Let's see. All right, try copying it again.
Okay. So let me copy it without the spaces into the command window.
Hit enter.
Sims requires.
Okay, requires symbolic math toolbox. So
I think that was the same error that. Okay, so yeah, Charles was saying that, and then Andrew's saying that. So okay, so I'll try to go to install the. I'll stop sharing my screen. Go to.
Okay. Probably in the installation, there's probably the ability to include to have everything, and by the way, of course, good advice from students here. I don't suppose you all have like a Discord or something that you can, like Charles has given good advice, and there's some other people giving good advice. I don't know if there's a way you can kind of communicate with each other, this kind of thing, maybe post it. Do you all have like I've heard of sometimes students, for classes, they create, what's it called, like a Discord or something? Oh, there is one, Ian? Okay. Charles says he can help people if they need help, and Ian mentions a Discord page. So I think on that note, I think you'll be okay. Now, thank you, Ian. Thank you, Charles. Thank you, helpers. Everybody who made good comments here, Andrew and everybody. One thing I want to mention here, I'll bring up the thing again. Let me just bring this up here, my MATLAB, because you're going to need this for some of the problems in your homework, and for the exam too next week. Let me see here. I don't want that. Hold on. I want to bring up the MATLAB. So let me get the application. Here we go. Okay, so I'm going to move this window over a little bit here. Now, if you notice here on the command line, you see that like F function there. If you click on that, it's a browser for help. So like, for instance, let's say you had to graph a surface, a function that involved the log, the natural log. Okay, how do you do the log in MATLAB? Okay, so you have kind of this basic function I'm giving you, but the function F, you're going to have to change it based on the function you're graphing, based on your surface. So okay, the log, it's not like the TI-83 or 84 calculator, probably. Type log, and you see here exponents and logarithms, and you click on that, and natural logarithm, and there it gives information on it'll give information on how to graph the natural log. And you can do that for sines and cosines and everything. So that's like the help. The help is very convenient. Okay. Are there any questions on that? And I'll make another comment too. You know, you can create, you know, in the editor, if you want to do like new script, it'll open up a new editor, and you can write code, and you can save your code. You can save as. I mean, there's you know, the editor is really the way to you know, write code. You don't want to be writing code like on the command in the command window. You want to be writing code in the editor and then copying and seeing that it works. And by the way, the editor, you see that green box on the top right? The green box, like the box can be green, it can be red. When the box is red, it usually means there's an error in the code, and you can like, there'll be like a notation, a little thing where you can see what maybe the error is. If it's green though, usually the code will run. So that's why it's good to use the editor. Question here? Question?
Yeah.
Yes.
This is probably just not, so this is an obvious question answer probably, but so when you denote e, e to the power of something, that's what you have to write on MATLAB is exp?
That's correct.
Okay.
That's right. It's different than the TI calculator, different than maybe Desmos. Yeah, MATLAB is its own language. And so you'll be learning some new things for sure. You'll be learning some new things.
Cool. Thank you.
Good. You're welcome. Good question, Mario. Okay. Are there any other good questions before I stop the recording? I mean, this is basically the main points I wanted to mention in for section 9.6. Okay, I'll stop the recording.